In the last lesson, we talked about centripetal force and centripetal acceleration. Centripetal force is when an object is traveling at a constant velocity and there's a force acting toward the center. It's defined as mass times centripetal acceleration. And centripetal acceleration is defined as velocity squared over the radius. Sometimes we refer to this velocity as tangential velocity because it's the velocity along the tangent of a circle. We also had the equation for tangential velocity, that is 2 pi r, or 2 pi the radius of the circle divided by t, where t is the time it takes to do one loop around the circle. Now we're going to apply these equations in some real-world situations. First, let's say we have a 945 kilogram car making a turn with a constant speed of 10 meters per second. The radius of the circle through which the car is turning is 25 meters. What is the force of friction and the coefficient of friction acting on the car? Well, our givens are mass, velocity, and radius of the circle. We're looking for F, which we sometimes write F with a subscript FRIC, or sometimes we just write a curly F to say friction. We're also looking for the coefficient of friction. For this problem, the best way to think about it is to draw your free body diagram. As the car is moving around a circle, it has the normal force holding it up and the force of gravity pulling it down. What's keeping it moving in the circle is the force of friction between the tires and the ground. And that friction acts towards the center of the circle. That is what's going to cause our centripetal force. So to solve this problem, after you've drawn your free body diagram, we're going to do the sum of forces in the x and the y direction. For circular motion problems, the net force is going to be the centripetal force. It's going to be the net force acting on the object. So the sum of forces in the x direction, which we normally say is ma sub x, in this case it's going to be m times the centripetal acceleration. Now we're going to add the forces in the x direction. We only have one. So that's the force of friction, and that's going to equal mass times the centripetal acceleration. We can replace centripetal acceleration with v squared over r. Now we plug in the values we were given to find the force of friction, which is 3,780 newtons. Now that we've found the force of friction, we can use that to find the coefficient of friction. And to do that, we're going to use our forces in the y direction, normal force and the force of gravity, because we know that the force of friction equals the coefficient times the normal force. So first, we're going to find our normal force. We know in the y direction there's no acceleration, so the sum of forces is 0. Normal force minus the force of gravity equals 0, which means our normal force is our weight. Or we can solve, and it is 9,261 newtons. Now that we've found the normal force, we can use our equation for friction. We have our force of friction and our normal force. So we'll rearrange it to solve for the coefficient of friction, plug in the values we know, and we get a coefficient of friction of 0.41. We're also going to consider a roller coaster. And if you watch in this animation, the normal force of the seat on a person in a roller coaster changes as you go around the circle. This is because our centripetal force goes towards the center, and if you're upside down, it's going to change what the normal force is so that it gets larger and smaller as you go around the circle in a roller coaster. Let's talk about this in more detail. Normal force depends on how sharply the track is curved, or the radius of the circle, and the speed of the car. As you're going up, your normal force is always perpendicular to the surface and force of gravity is down. If you were driving on the top of a circle, you'd have gravity down and an applied force down. If you were driving at the bottom, you'd have your normal force going perpendicular and your force of gravity going down. The two variables that affect the acceleration are going to be velocity and the radius, and that in turn affects the net force. So let's look at a car going at a constant velocity around a circle. We always have a net force towards the center because it's moving in a circle, and our centripetal force goes towards the center. If you had a car that was upside down like this one, at the top, your normal force goes perpendicular to the surface, so it goes down. Your weight also goes down. and your overall net force is towards the center of the circle. At the bottom of your circle, your normal force goes up because it's perpendicular to the surface. Your force of gravity goes down, and your overall net force goes up because we're moving in a circle. So you can see that the magnitude of the weight has stayed the same, but the magnitude of the normal force has changed depending on where we are on the circle. So if a roller coaster travels in a circular path, at what point, the top or the bottom, should the seat exert the greatest force on the passenger? The force that the seat exerts on the passenger is our normal force. So if you remember this picture, at which point is the seat exerting the greatest force is when is the normal force the greatest? And that's going to be at the bottom of a roller coaster. And when you go on a roller coaster, you can feel this. You feel like you're being pushed down when you're at the bottom, and you feel more weightless at the top. Now let's do a problem with some numbers. A roller coaster travels in a circular path. Assume the speed of the roller coaster is 10 meters per second at the top of the loop of radius 8 meters. What is the force exerted by the seat on a 70-kilogram passenger? And we're looking for this normal force is also going to be called the apparent weight of the passenger. Now, in this problem, the only object we're looking at is the person. That's going to be our object that we draw our free body diagram. The person has a normal force exerted on them from the seat, they have their weight, and then they are going to result in a net force towards the center of the circle. So remember, for circular motion problems, the net force is the centripetal force. In the y direction, we're going to add our forces together. Now notice, all of our forces are pointing downward, which means we're going to use negatives for these forces. In the y direction, we have a negative force of gravity, a negative normal force, and added together we get a negative centripetal force, or negative MAC. We can replace Fg with mg, we can replace centripetal acceleration with v squared over r. And we're looking to solve for normal force. So we're going to rearrange the equation to get our variables separated. Now we're going to plug in values and solve for normal force. And you get a normal force of 189 newtons. That is the force exerted by a seat on the passenger at the top of the roller coaster.